Okay. Yeah, thanks. Thanks for invitation and thanks for organizing this workshop. I'm Jiasen Niu, a postdoc from Leiden University and University of Munich. And today I changed my topic a little bit to the short-noise microscope, because actually my result is focused on cuprates. It's also not very related to the quadratic pairing. But I want to introduce our technique. They call short-noise microscope, and I hope our technique can help you in this field. And first, I want to acknowledge my postdoc supervisor Milan, because his family issue, so he will come on Wednesday, so he changed his talk with me. And I also thank all my team members, especially Mylan. She did a lot of work in this project. And thanks all my collaborators, Genda, Imer, and Yasla. And we were in the Leiden University, and this year we are moving to Munich, but it's not finished. I guess many people know this story. It's a very long story about this one. So today in my talk, I will first show you our technique. It's called short-noise STM, or short-noise microscope. It can detect Cooper pairs. And then I will show you one of our newest results about the measurement on the cuprates. I think, in the BCS series, we have Cooper pairs in the superconductivity state, but usually it's very difficult to directly detect these Cooper pairs. We always use some indirect way to measure it, like thermal transport and like measure density states. But today I will show you there's one technique is called short noise. It can directly detect Cooper pairs, detect the effective charge of the Cooper pair. So what is short noise? When we do experiments, for example, usually we measure current or voltage. We have raw data like this. We have fluctuation of current versus time. Usually we measure average of this current, we call it current, but we also have the fluctuation, the delta I, this is a noise. There are a lot of kinds of noise, most of them from equipment, from environment, so that's why we want to average to get rid of them. But interesting thing is there are some kinds of noise is from sample itself and can give us extra information. There's one kind of noise, it's called short noise. It's from the discrete nature of the electron charge. We can simply understand it like, for example, if we have metal, we have electrons, and when we measure current, actually we measure electrons one by one, and every time we get one electron charge, we have one current fluctuation. But if we have the Cooper pairs, every time we measure two electron charges at the same time, then your fluctuations should become bigger. In this case, if you can measure the fluctuation, amplitude of fluctuation, you will find that you can measure the effective charge. In the theory, we can calculate the short noise power S is proportional to the charge Q, the current I, and also proportional to the 1 mass tau. Tau is the transparency. It means your possibility that your electron, your charge carrier, can transport. So usually in the experiments, we will fabricate some tunnel junction to make sure the transparency is small. You can go to the simple equation. It's the S equals 2QI. In this case, if you can find the way to measure the noise, you can measure the charge. In the experiments, what we do is usually we measure the raw data current, and we do FFT. For this one, we will get the noise power S, and we will change the current I, you will get this linear behavior. We should change the current I because we have many background, so you make sure we don't measure the artifact. We need to know we only measure short noise. And from this linear behavior, you can know the charge. If you have one E charge, you have electrons, your slope will equals 1, like the yellow line. If you have Cooper pairs, the slope will equals 2. You will have the blue line. This short noise, it was first used in the fractional quantum Hall system to measure the fractional charge. It was considered as one of the smoking gun for the fractional charge. And these years, we start to use it in the superconductors. In our lab, what we do is we combine STM with noise, and we have short noise microscope. Now I don't want to explain how it works, but you may feel a bit weird that why we make it so complicated. It's like because we know STM is not a very simple method, and noise is also very difficult. We need a very nice low temperature cryogenic amplifier because signal is very, very small compared to the traditional method. It's usually like 3 orders smaller than the conventional signal. But why we make it so complicated? This is because if we go to the superconductors, there will be some special challenges. The first challenge is that actually the noise on the superconductors, it depends on the geometry. Different geometry can give you a different result. if you look, if you are familiar with this field, you will find that when people start to do the experiment on superconductors, there are a lot of contradictory results. Somebody says that, okay, I can measure Cooper pairs. Somebody says that, oh, sorry, I cannot. But actually, the reason is because of the geometry. The geometry can give you different results. We can simply understand, for example, this equation I showed you. Usually, we will, it's shown the power at proportional to 2qi times 1 minus tau. Usually, we will fabricate nice tunnel junction to make sure the tau is small, and then it will become simple. But if you use this thing in the superconductors, the results will be different. We can simply understand it like this. It's like when we have a tunnel junction as an ion tunnel junction, usually we will have anti-reflection when we have an inside span gap. And this anti-reflection will give us, actually will give us 2e, the short noise equals 2e. But we will still have a little bit crispative contribution because of temperature, because of defects, because of magnetic field. And this thing will give you 2e contribution, or 1e contribution. And the results we measure actually is average of this 2e and 1e. And if you do some simulation, you will find that unfortunately there will be another thing happen, as this 2e contribution is proportional square of the tau, and 1e contribution is proportional to the tau. And in this case, if you try to make a very nice device, you will surprise this contribution. You can do some simulation to say that if you have the typical microscopic device, your noise will be like it will saturate around 1e. You don't have any charge 2e. And only when you reach this point contact geometry, you will have the typical result as what you want to say. You will change charge, your effective charge will change from 1e to 2e, and you reach to 2e inside spin gap. And we can estimate the transparency in the previous work to see whether this can explain the contradictory results in the past. We can find that it's quite okay. If we estimate the transparency in the previous work, we can find that somebody they have very nice insulated layer. They make sure there's no pinholes. There's very nice. They deposit quite safe. And then if you make your device become good, actually you go to the wrong way. It's like you will have charge equals 1e. And somebody actually their insulated layer have some pinholes, and usually we will think that this means it's a bad device. But actually that one will help you to measure this 1e. But it's like this means if we really want to do the experiment on superconductor, we really want to measure the Cooper pairs, we need to find a way to solve this problem instead of just try randomly make some insulated layer. A good thing is we can use STM. STM can help us this. Because in the STM, we only have single channel and we can control the tip sample distance. This means we can control the transparency. And then we can overcome this problem. And also STM can give a nice clean area because we only have vacuum area. So we don't have defects, don't have intermediate state in the vacuum. This is, I did not tell you, but this actually is very important for the noise because the intermediate state can give you the two-step tunneling process. It can change the result a lot. And the STM, it can overcome by itself. And a good thing is that in the STM, we can do the noise because we have tunneling current in the STM. If we measure fluctuation of this tunneling current, we can measure the noise. And we don't lose the spatial resolution. So this means we can also have atomic scale effective charge measurement. So then in our lab, we try to combine these two things, let it reach to a new method. It's called short noise microscope. But if you, it's like if you really want to do this one, you will have a second problem. The second problem is like the STM is not so simple. You have a lot of extra noise in the STM. You have mechanical noise, you have 1F noise, and the bandwidth of the STM is so low, so you cannot really measure the noise. To overcome this problem, what we do is like we build a homemade cryogenic amplifier. And with this amplifier, we can have a readiness for circuit at megahertz, actually at 5 megahertz. It can help us to get rid of the low frequency mechanical noise from STM, and we can really only measure the short noise. And this is also quite important. So that sometimes, in the previous work, people report that they measure the Cuckoo's effective charge very high, but it's not true. It's from some artifact. Yeah, if you are interested, we can discuss after this talk. I will not talk about it now. So now, with the short noise microscope, we can start to do the experiment. We first do it in the conventional metal gold, and you can find that it's work quite well. You have qubits 1e linear behavior, so you only have electrons in metal, it makes sense. And then we can go to superconductors. In the superconductors, first at the outside swinging gap, you also have 1e because your quartz particle, it also makes sense. If you go inside swinging gap, you can clearly see that your effective charge change from 1 to 2. It's overlapped quite well. So this means it's true that a short noise microscope can help us detect Cooper pairs, detect the effective charge of Cooper pairs. But actually it's from reflection. And then I will finish the first part. It's like now we know we can use the short noise microscope to detect Cooper pairs, and then we can do many interesting things. There's one thing is we can do is we can detect the possible preform pairs in the cuprates. Although today's talk is not about cuprates, but I guess all of you know this one. It's a typical phase diagram of the cuprates. There's one phase called pseudogap. It's a very interesting and quite important phase in the cuprates, and it can be measured by many different techniques like RPS, STM, or other things. And we have with short noise microscope we have STM, so we can still do STM now. They are independent. We can do it together at the same time actually. And this shows the typical spectrum we measured on the biscope below the TC. You can see you have two energy gaps. One has a large energy gap. It's called the delta PG, the pseudo gap. And inside this pseudo gap, you have a small kink structure. It's called delta kink or delta IC. It's believed to be related to the swinging gap. And when your temperature going up, this measured below TC. When your temperature going up, the swinging gap will disappear, and the pseudo gap will persist above TC. You can also change the different sample with different doping, and this two energy will also change with the different doping. If you summarize it, it will show a similar phase diagram with the temperature. The swinging gap will show a doping feature, and this pseudo gap will show a linear behavior with the doping. But it's like we still have this question about what is the pseudo gap. There are a lot of experiments and theories to try to answer this question. We can very naively divide them into two different cartoon scenarios. In the first cartoon scenario, it means that we believe that pseudo gap is related to local order, like charge density wave or spin density wave or similar local order. In this scenario, it means that only the superconducting gap is related to the pair wave. You only have Cooper pairs below the swinging gap. And in the second scenario, it's like it believes that you have preform pairs. It means when your temperature energy going down, you have some preform pairs. They don't have phase coherence, but you already have Cooper pairs, so you lose density states and give it gap. And in this scenario, it means that you already have Cooper pairs at the superconducting pseudo gap energy. And you can find that in the experiments, usually it's not very easy to distinguish the two different scenarios. But if we can find a way, can directly measure the effective charge, we can know this one very clearly. Because if you can measure the Cooper pairs here, it means you have preform pairs. But if you cannot, it means you don't have preform pairs. And as I said, the short noise can help us. Short noise can measure the effective charge, and it can solve this problem. So we can try to use our technique in the short noise. We first do it in the biscope, and what we expect is that we want to try to see this change at which energy. It's at superconducting energy or at pseudo gap energy. But if you really directly do the experiment, you will have something like this. You can find that it's quite different with what we expect. It's like if you calculate effective charge, it's reflected around 1e. So this is quite weird, right? It's like we want to say, okay, we have Cooper pairs, but it turns out that we don't measure any Cooper pairs. We don't have anything. Actually this is because actually the Cooper is more complicated. It's like Cooper always make our life become hard for the experiments. So it is because in the result I showed you before is an S-wave superconductor. It have hard gap, and on the Cooper it's D-wave superconductor. It have nodal gap, and because of this one, you have some quartz particle inside swinging gap, although it's superconducting. And in this case, in the experiments, what we measure is we measure the fluctuation from the whole current. So this means we measure fluctuation from both Cooper pairs and from the electrons. And your effective charge measured by experiments will be average of these Cooper pairs and quartz particles. And then it will be surprised from 2e. We can do some simulation for the D wave and S wave. You can find that for the S wave, it's clear you change from 1e to 2e, this is effective charge versus energy. And for the for the D wave, this D wave is calculated for the single gap scenario. And you can find that it's much smaller than the S wave. And if you can compare the experiment results with the theory simulation, you can find it can make sense. You should not measure anything with now, but unfortunately, actually, this is already one of the best resolution at that time. But you know, it's like this means it looks like no hope, but it doesn't mean we should give up. And in our lab, what we do is like we spend a lot of time to try to improve our setup, to improve the resolution. We build the second and third generation of amplifier. It shows our newest system. It have a homemade STM to make sure it's very stable. It have a homemade amplifier to make sure it have very good resolution. And if you compare our newest resolution with the old one, for example, if you do the experiment, same experiment on gold, the blue dots is the new one, and the yellow is the old one. You can see that it's become much better resolution. Actually, it become more than 20 times better than resolution. And we can also estimate the resolution of the effective charge now, the sensitivity of effective charge versus average time. In the experiments, we find that actually at a reasonable average time, about more than 5 minutes, we can already have an effective charge sensitivity below 0.01 E. It means if you compare it with simulation, such a good resolution is already, you know, it's like worse. We have another try. So we start to do our real experiments again. This time we choose a visco 2212 as the material because it's easy to clip, easy to measure in the in the cuprates, in the STM. And this shows the typical topograph we have. You can see a clearly supermodulation. It's a very nice sample. We get it from Ghana. And before I show you our experiment results, I want to talk about what should we expect for these two different scenarios to make sure you can understand the results. And yeah, for the local order and preform pair scenario, if you remember here, actually there are two curves for the D wave superconductor. And actually these two curves is already calculated for these two different scenarios. But I don't want to say that what in experiment we want to measure is we want to measure the absolute value of these two curves. It doesn't make sense, you know, it's like because this absolute value really depends on the parameters, and the parameter we get from RPS. But you know, it's like it's not for our same sample, right? Maybe a little bit different. But if we zoom in on this part, you can find that actually the effective charge shows similar behavior with the S wave superconductor, although its value is much smaller. For the S wave, at the pair energy at the superconducting gap, you change from 1e to 2e. For the D wave, you will still have some very fast increase, we call noise step. And this is because, you know, it makes sense, right? You have Cooper pairs at this energy, so you should increase very fast at this time. And in this case, if you add the preform pair scenario, you will have this step at the pseudo gap. But if you add the local order, you don't have pairing, you don't have this step at the pseudo gap, you will have step at the kink. Yeah, I know there is very tiny, but if you zoom in this part, you will see actually there is another step there. And so this means we can simplify our experiments to what we want to measure to. We should measure whether we can measure the noise step and where is this noise step. And yeah, in our experiments, we measure 4 different samples with different doping from optimum doped to the underdoped. And I will first show you the results with the underdoped sample called underdoped 60K. The 60K is the TC. And first, this is the spectrum. It's a typical spectrum. We have pseudo gap and swaying gap. And this is the noise. You can clearly see that first, we see this step. You can clearly see that it's not fluctuate around 1e, instead it increases step. So this means that with our very good resolution, we can measure the noise enhancement successfully for the first time. And the value is a little bit smaller than 1%. It's similar with our expected in simulation if you compare with simulation. And then, if we compare this pair energy with the spectrum, it means that you can find that it overlaps very well with the pseudo gap energy, and already start at 50 millivolt. So this means you already have the pair energy at 5 millieV. It's a very large energy, and then we can already make our first conclusion now. It's like we can find that the pseudo gap is related to pairing. There is no competing between the pseudo gap and the pairing. And yeah, it's a. And now, if you remember that we have STM now. And with STM, we don't lose the atomic resolution, so we can have the atomic effective charge measurement. And for the BISCO, it's very spatial inhomogeneous. And if you measure for one sample at different area, you will find that you have very different pseudo gap energy at different area, but superhelium gap is similar at all area. And for the noise, this means that if we believe that the pairing is related to this energy, it means that maybe your pairing is also spatial inhomogeneous, it's heterogeneous. We can try to confirm this experiment by experiments. And we can find that actually for different, this also we measure on same sample at different area, you have different spectrum and you have a different pseudo gap. If you do the experiment data, you can find that your noise step is followed very well with the similar behavior. When your pseudo gap increase, your pairing also increase. So we can extract the pseudo gap and with the superhelium gap, with the noise step, it's calculated by the gradient of the effective charge Q, and summarize it, you can find that it's overlap very well with the linear behavior. So this means that if you first it confirms that you can have pairing at the pseudo gap energy, but it also tells us that your pairing energy at the spatial is really inhomogeneous. It's really heterogeneous as the pseudo gap spectrum. So this means that actually we can directly know the pairing energy with the spectrum at all the atomic area. And finally, it's like, as I said, we measure many different samples. And so for different samples with different doping, like for example, if we change from optimum doped to underdoped, our pseudo gap energy will increase. So how about your pairing energy? I will skip to show you the results one by one and direct show you the summary of the results for all the samples. You can find that all the experiment results follow very well with this linear behavior. So this means that actually the different doping they can show similar behavior. And when you change from optimum doped to underdoped, actually, yeah, if you say optimum doped is this part and underdoped is this part, actually your maximum pairing energy will increase instead of decrease. And now, actually, we can ask a little bit more questions about, for example, how about the local order thing? Actually, we don't know. We don't really measure the local order. We only measure the pairing, so we cannot exclude the possibility that they are intertwined with each other. And we can also ask about what limit the TC. If you see our results, you can find that actually when you change from optimum doped to the underdoped, your pairing energy will increase, but your TC is decrease. So actually we can think about that. Actually, it's because of the steepness, the coherence limit of our TC. If we want to go to higher TC, maybe we need to find a way to increase this one. And yeah, and also I want to mention one more thing about how about above TC. It's like I want to mention one thing is that actually all our experiments is measured below TC instead of above TC. We measure 4K, 2K, and 300 milli-K. We try 3 different setups to make sure it's not from artifact. And this is because if we go to higher temperature, we will lose the noise resolution because of thermal noise will increase. But a good thing is in the STM, we still have 2 energy gap below TC, so it's still good for us to distinguish these 2 different energies. But it's like we can try to find a way to overcome this problem. It's like we can get a sample with a 0 TC sample. In this case, we can still measure above TC. In the previous work, people find that they can measure the some pseudo-gap structure in the sample with 0 doping, and likely it indicates that we have the local pairing. And we are trying to confirm this with our experiment to see whether we can really measure the Cooper pairs with a sample with 0 TC with very low doping. We already have a little bit results, but yeah, it's not very nice to show it now. I hope next time I can show it to you. And yeah, finally, I want to give you a little bit outlook. It's actually outlook is more related to this workshop. Yeah, when we combine the short noise with STM, we can have the short noise microscope. It can help us with measure the effective charge. It can do many interesting things. The first thing is, as I showed, we can measure pseudo gap, and we can also try measure some maybe some artificial effective charge. We can control the effective charge in the conventional superconductor. We can make it become smaller than 2e, go to the any value we want because we have STM, we can control it. It's very nice. And we can also measure something above 2e. It's like, for example, this is one of our newest results. You have result effective charge 1e, 2e, 3, and yeah, it's not go to 4e, but it's enhanced a little bit and then go down. Now we already understand it. It's because of the temperature. But this is not a really 4e system. It's just a confirmation to check that we can measure the 4e charge if there is really a 4e system. And I hope yeah, we can contribute, we can measure sometime. Because I think Milan will talk about more about this one, so I will skip it here. And also it's like, now we find that we only measure cuprates. How about other superconductors? So you can in other superconductors, like iron-based superconductor or other materials. Yeah, we are working on this one, but this is a very long story. I also will not talk about anything here today. I just say it's like, yeah, we can think about this one. And finally, yeah, I want to give you two take-home messages. One is that we can have short noise microscope. It can measure the pairing. And with this one, we can do many interesting things. One thing is we can detect the pseudo gap, and we find that the pseudo gap is related to the pairing in the cuprate superconductor. And thank you. Yeah, thank you very much.